Just want to check the camera first. Did you record? What? But I think if we hide it, it should be fine, right? But
Why is that?
Because it's looking at the camera and the camera's looking at the camera.
exactly.
It's recording the screen, right? How many
It's recording. Yeah. Infinite number.
Oh my God.
Cool. Hello. Good. So yesterday was data storage technique 1, and today we're going to start with databases, which is data storage technique 2, whatever we explained yesterday, plus we're going to talk about different types of databases. We're going to talk about two main types of databases, SQL and NoSQL. This sprint, so mainly we have two lectures here, one in the morning, one in the afternoon. But this is just a sprint intro. This is just like 3-4 slides. We're going to talk about sprint in general, what's going to happen. But mainly we have two lectures. The morning lecture is whatever we started yesterday. We're going to build NoSQL database and talk about how we built it. You don't need to pay that much attention to it. It's a little bit tricky. But you should get the idea of why we're using NoSQL database. And then we're going to talk about different types of databases. And in the afternoon lecture, we're going to talk about more the schema, how to use the SQL database. Now, I want to open the sprint for you. I think it's important to understand what's the sprint about. So you have two courses here, school and databases. Let's see school. So that's school. It's an introduction to SQL. So what's that? Gives you a portal. You follow the instruction. You read and follow the instruction in order to try SQL language. SQL is a language. So it will give you a portal to just type some SQL commands and try them and see the results. Okay? That's the point of it. So to practice some SQL, it will use something called SQLite. This is our DBMS, Database Management System. SQLite. There's many types of SQL. SQLite, MySQL, PostgreSQL, many SQL Server, many of them. Okay? So it will tell you how to set up, how to use the schema, what commands you should run, and then it will ask you to do stuff here. Okay? It should be super quick. Don't spend that much time on it. Just follow the instructions. Now, the other part is databases. And this is where you set up your own database. We'll give you a database file that has some tables in it, some schema in it, and then you need to set it up and add to it, or interact with it directly. So you get it from the repo, and then you just set it up as you do in your project. So if you want to use SQL in your project, this is your reference. Okay? So databases sprint. And of course, it has some advanced content. I expect some of you guys, if you get the lectures, you should get to the advanced content. Okay? You might not, which is fine, but if you get to that, would be great. Okay, let's go back to the lecture. So, sprint intro. What are we trying to do here? So, dive into the world of persistent storage with databases. Okay, so database is a way to do data persistence. Spend some time learning, practicing database. Okay, and then you will apply whatever you learned from the first course to create your own MySQL database and apply it to your Chatterbox application. Okay? And from there, you will learn about something called object relational mapping. This is very important topic here. ORM, they call it ORM, object relational mapping. This is one of the interview's questions. What's ORM? Have you heard of it? You'll say, yes, it's object relational mapping. What does it mean? Can you give me an example? So pay attention. Next, we'll learn SQL for sure. So before worrying about setting up a SQL server, you must attain certain level of understanding the SQL concept. What's SQL? And so this is we prepare the SQL-focused companion repo. So it's a repo that you will set up your SQL and practice the SQL commands. And then, one of the objectives is understand the schema. Can anyone tell me what the schema is? Have you heard of it? It's not used a lot.
Say something like structure.
Structure, good. It is. It's a table. Yeah, it's a table actually. It's as simple as that. It's a table and a database. We'll see what it is. Okay? So we work with a schema visualizer to implement these tables or schemas. And then you will work with ORMs, the second half of the sprint. You will know how to convert the idea of the way you see your problem into tables and databases. And this is the core concept of databases. So you will work with an ORM called SQLize by refactoring your chatterbox implementation. You might not get to this part, which is fine. Okay? Later on, in the full stack sprint, we will revisit this. We'll use NoSQL. So there's no, if you notice, there's nothing about NoSQL databases here. It's all about SQL databases. Okay, but in the advanced topic, there is NoSQL too. If you get to that part, that's fine. If you don't, you'll get to it in the full stack review. So you should go through the README for both sprints and the school companion repo, which is will give you again a visualized repo to practice school. It will take you command by command.
Can you solo mini solo sprint?
No, nothing solo.
With pair?
I think with pairs, yeah. You guys talk about but I think with pairs. Yeah, so don't skip any section. It's very important to complete each section. I think you can skip, but don't skip. Not sure, but I think you can. And then, after we take the lectures, you go try the problems. Okay? Cool. That's all about the sprint. Now, let's go to the lecture. This is a long lecture, heavy lecture, about 100 slides. Okay? Gonna skim through. I don't want to talk about a lot of details because this is about how we build a NoSQL database from scratch. It's going to talk about the idea of data persistence.
Yesterday you told us we're going to implement MongoDB, which is NoSQL.
Exactly, we're going to do it now.
So instead of slides.
It's slides.
Instead of slides, I mean.
It doesn't work because MongoDB is already there. We're not going to type it now. We're not going to code it now. It's going to take a week. But I'm going to talk to you about the idea, how we create MongoDB. No one in the future will ask you to create a NoSQL database at all. Okay? Because it's already there. But here, it's just about the idea, why MongoDB is built in this way. Okay? We talked about some problems with data persistence yesterday, and these are some of them. And we said we need to make sure, like we achieve data persistence. We need to solve these, which is enable information to be addressed in multiple ways while maintaining ideal time complexity. Asking the database many questions with good complexity in different ways. Okay, can store more data than in the memory, because hard disk has more memory. Okay, more storage. Does not rewrite all state on every change. We'll see what that is in a moment. Prevent information lost during the core failure. This is like we gain it for free. So let's talk about the first concept. How to address data in multiple ways with maintaining ideal time complexity. The ideal, what's the ideal time complexity by the way?
Linear mean?
Constant, good.
I mean, constant is impossible.
It's ideal. We're gonna get it. We should get it. Yeah. Let's see. So we're gonna talk about the fourth most useless messaging app, which is the app that we use. It's useless. So this is the app. Messages, they are in an array. So we have messages, each message object as a user who send a message, a chatterbox, okay? Text and the room. So the messaging app has different room where you can talk to each other, okay? So this is our app. Very important to notice a couple of things here. Who sent the message, in what room, what's the text, and the order. The order of the messages. The order of the messages within the room and the order of the messages within the app. This is super important. We need to maintain that, okay? So this will get bigger and bigger and bigger and bigger, and then at some point we should save this in the hard disk. So we should do data persistence. And this is actually our problem, to do it this way, okay? So we should find a way to, as this gets bigger and bigger, we need to save it somewhere in the hard disk. So recalling like each data, if it's in the memory, we can easily say messages of some index is this message, easy. So that's accessing the data. So whenever we want to access the data in the memory, we can give it just the index and we'll get it. It's constant time. That's easy. But the problem happens when we save it to the hard disk. What we talked about yesterday. So what's the complexity of finding the message was sent from the room name group? I ask you to find messages sent from room name group. What's the time complexity of it? N. Why N?
Because we're going to have to loop over the rooms and then check which room.
Yeah, you cannot avoid the big O of N in this case. Because it could be, the worst case could be the last one. That's not only the problem, what's the other problem? There's many of them, right? So you need, even if you find it in the first one, you need to continue to the end. So it's always big O of N, okay? So that's big O of N because it's a loop, all right? Can you think of a data structure that gives us big O of 1 instead of big O of N? Hash table, good, yeah. Hash table gives us big O of 1. We don't need big O of N. So, cool. So, good question. He said, why do we continue?
Okay.
That's roof, right? How many messages for roof? We have 1. How about lobby? We need to check all of them then. All right? So if we find a way to use a hash table to say, okay, this is a hash table instead of just putting the messages in an array, just pass the room name as a key. What's the value?
The messages in that room.
The messages. Not one message, messages. What's the data structure we should use here? So I want to say, these are the messages of room. I'm talking about rooms now, only rooms, okay? This is the message of room. It's an array, right? So we need to put some kind of an array. In this case, it's 1, but in other cases, there are many of them, so we need kind of arrays to say, this array has pointers, for example, to messages. Same thing for other stuff. Okay? We do the same. So we say also park, we pass it to the hash table as a key, and we say park has this array as a value, which is pointers to the messages of park room. and so on and so on and so on. Okay? So almost the same.
If you're gonna send like from the same user to message, like you're gonna pass it and create another array for each user.
Can you repeat this question?
Okay, I'm sending the first message on lobby park and the other message on the lobby the room, sorry, roof.
Yeah.
So I have array to the person also.
Cool. Wow. You're reading my mind. Good question. He said, like, I want to send messages to different rooms. So I need a way to represent data sent by me, not only by your room. And this is actually part of our problem. Cool. We'll talk about it in a bit. So in fact, every message that gets added also, it will update the hash table here. We need also to update, okay, I added the message to another room, so we need to find the key, go to the array, update the array here and say, okay, this now points to a new message in the messages array. Okay? So we should keep it. Every time you delete, every time you add, every time you edit, we should go and update this hash table, the content of the hash table. Okay? So this is just the way. What are we trying to solve? We are trying to say, okay, find the messages that's sent in this room. That's it. That's one piece of the problem. Not only we need to update the hash table when new message to be added, we also update the hash table when a message is changed too, right? So we want to check like this message, some message changed. We need also to update the hash table to say this message has been changed. Now, when we delete a message, we do the same. So every change, what's a change? So change, be familiar with this term. CRUD. CRUD. Can anyone know what CRUD is? Well, this is just, some people use it. Yeah, cool. Create, read, update, delete. So this is, if you want to do any operation on a specific piece of data, you say, okay, do CRUD for it. Like, make sure it does create, read, update, and delete. So in this way, we can do all of them using this technique. Cool. It's very common to use multiple data structures. So this is a very common solution for a problem. We're using two data structures here, a hash table and array to solve this problem. Okay? So and this gives us like find messages of specific room. It's bigger of one because we're just saying here's the array of the messages directly without skimming it through. Okay? Well, some of you say, okay, well, this is an array, I need to look through. But this is like a different level of complexity. We're just saying now, give me a direct access to the messages of a specific room, and they just give you the array without asking you to go to here. Okay? Without asking you to go to here and find all of them. I just tell you, here it is, this is the array, directly. Let's take a brief tangent and explore another option. Let's see other options. The bigger of one lookup by room name and can be solved using another technique. Do you have another technique here? For the room, yeah, it's exactly. We can solve the same problem with another technique. Yeah. Well, it could be the hash table, but not the array, maybe. Objects, yeah, could be.
The messages.
So you want to say lobby as a key,
Yeah, and some value
the value of the message. Let's see what's our solution. So it's kind of the same, but instead of, we could have chosen to use an object instead of an array. Okay? So messages here, every message is a key instead of a hash table that, in an object that points to an array there, but still the same, right? We did not change anything. It's still an
organized data.
It's just a way to organize data. So it's still the same. While this is a valid solution, it has significant drawback. Can anyone tell me what's the problem here?
Object itself is built over the hash table.
It's what?
The object, he built it over the hash table.
Yeah,
It's the same.
it's the same. So nothing changed. But is there another problem with the solution?
The sequence of messages coming to the like.
Amazing.
It's not gonna be like time.
Yeah.
So it's gonna be different sequence.
So you don't, in this way, you guarantee that the order of messages within the array, within the same room is correct, but you don't guarantee the order of messages in the chat app, right? So the first solution was even better. Now this is not working. Think. So let's go back to our original solution. At some point, we may discover that our application needs to address message data by different attributes, such as user, the one you mentioned. Like we need another way. So this solution was better than the second solution, and then we deleted the second solution, going back to the first solution. And how do we address messages by user? Instead of, we need to make another hash table. Yeah. So we make another hash table for user, and we do the same. We say these are messages for user Hamela, and so on. So we keep doing that. Okay? So different hash table. This will guarantee big of one. It will give us everything we need, and our life is easy now. Okay? Hash tables, as demonstrated here, are more commonly referred as as indices. So what we're doing here, we just like saying, so this will give us indices to the original array. So this is the index of this array, and so on. An index can dramatically reduce the time complexity of finding data by frequently used traits. If you recall, the speed comes with the costs. So we need, every time we need, it guarantees the index just gives us direct access, and the time complexity is great, but could be other problems. Let's see what's going on here. So there is also drawback. Yeah, time complexity is great here, but indices must maintain whenever messages are added, updated, or removed. This is important here. So whenever you do an action, you want to guarantee the same order and nothing has been changed. Nothing has been destroyed. Let's say. The more indices you create, the longer it takes to apply a change to your data. Let's say you want to remove something, you want to add something. This might cause some problem here, like changing the add, changing the index, for example. If you want to remove something, the indices could be shifted to the left, and this will go here and update everything in the hash table.
Which will take a long time.
Did you get my point? Let's say we deleted this. What's going to happen?
The references are all going to change. The hash indexes or the hash itself functions.
Yeah,
Change the order of it.
because all of these messages should be shifted to the left. And that means we need to go here and update everything. And you update them twice. You update them in room and in user hash tables. That's also a drawback.
What if we just leave it empty or something instead of shifting?
That could be a solution too. Yeah. There's many solutions there.
As an empty spot, like empty.
Empty, like we mark it as deleted. This is deleted. Yeah, could be a solution. Okay. Again, the purpose of this, we're just figuring a way to solve a problem. We're gonna give you the solution at the end, but this is just like conversation to see how people came up with this MongoDB thing. So we have completed our exploration of addressing data using ideal time complexity, which will solve the problem. This is one last refactor to do before we can start applying these concepts to data persistence. We need to do last thing. So quick review. If you remember, if you recall from yesterday, we talked about this. We said, well, we have some memory here, and this is an object here, so we have some message. And this is the message who sent the message, the text, and the room. We need to save this in somewhere in the hard disk to apply the data persistence. We said what we do, what's the format of data here? String.
JSON stringify.
JSON string. Okay? So JSON format as a string. So if you recall from part 1, memory locations are not serialized. So we need to serialize this data. Save them as JSON, serialize them in the hard disk. Understanding this concept is critical. So it will help us do the refactor. So let's go refactor now. So this solution works in the memory, but now we want to refactor it to do something else, to be serialized in the hard disk. So we must, in order to persist this data in the hard disk, we must serialize all 3 data structures, right? Must serialize this, and serialize that. All of them should be serialized. That's serialized, like convert them to JSON and save them as string in the hard disk. Because it's not memory anymore, right? We want to move this data, save it in the hard disk, because tomorrow, if you open your computer, you want to see this data again. Otherwise, it will be deleted, right? That's the data of data. That's the idea of data persistence. Serialization is converting this data into JSON as well as string and add it to the hard disk. And tomorrow, when you load it to your memory, it will be converted back to objects. Okay? So let's see what's the problem here. The messages collection and both the user and room indices. Remember, only value gets serialized. So we serialize the values. What values are indices referring to here?
Indexes in the messages array.
Are they indices? Are they something else?
Object.
Objects? What do you think? Objects. So what data is held here in the array? Indices, right? Could be. Yeah.
Just a reference.
Think of it, the data before you save it to the hard disk and after you save it to the hard disk.
Oh, you mean in the memory.
Yeah. Let's see. You don't need to answer this question. It's okay. So indices refers to the message objects themselves. Remember, not the indices in this case.
Yeah.
Okay? So to serialize an index means we must serialize the message object too. So whenever you serialize the index here, because indices refer to message objects, so this refers to some object, and this object itself should be serialized too. Why serializing message objects from indices is an issue? So you take some message from an index and you want to serialize it. Why this is an issue? You don't get the question. So indices refer to message objects, right? Every index here refers to serialize an index. You want to serialize every index here. Okay? It means we must serialize the message object too. You want to serialize the message object itself. Okay? So you want to serialize both ways. Okay? Why serializing messages objects from indices? From the indices is an issue. So you want to take an index, go to the message, serialize the message itself, the object, and go to the next array, for example, read every message and serialize it. Why this is an issue?
It's,
Is it only pointing to the message, or does it actually have the value?
It's pointing to the some index in this array.
Does it actually have the message inside the array?
Yes, it does.
It does.
So
Both
JSON
ways.
stringifies anything.
Stringify it.
It's arrays and objects, or objects and arrays.
That's
It should
cool.
work.
Yeah.
So why would it work?
But when we say this index has been serialized, to specific value that's saved in the hard disk.
You need
Does
an
this
index.
match whatever is serialized here? Yeah, kind of. You want to serialize an address maybe, not an index. This is solved. You don't worry. Like we'll solve it.
My question is, why couldn't we just stringify or serialize the array itself and just ignore whatever's inside?
Ignore. So we keep. You mean we keep the indices as is?
Yeah, just
So we just serialize them.
that array as a whole.
And when we read them back, we're gonna end up with this solution. But people were trying to do something else. Let's move on. I think, yeah,
I'm lost.
you're lost.
Yeah.
Who's lost? Woo! Why? Just don't keep. Okay.
Is the serialized things?
Yeah. So again, did you guys understand before serialization? Did you guys understand this topic
The hash part?
in the memory? What's going on here?
Yes.
Who's lost till this point? What are you lost? Do you have a specific question?
What do you expect?
Okay. So think of it this way. Think of this as an object that points to, that has keys and values, and each value is an array of indices. Is that easy to do? That's easy, right? So this is the idea of hash table. So we don't save the actual data inside the array here, but we save only the indices of the array here. And so we have three objects now. So this object tells you what each room has in that. Well, this is a hash table. Think of it as an object. It's like, well, we call it a hash table, but think of it this way. This could be represented by, let's say, room equal park column array indices index 103 205 and so on, and then lobby same, some indices and so on. That's it. So if you want to get, like if I ask you what are the messages inside park room, you go to room, you find the room of park, it will give you an array. And that's an array of messages. You go to here and get each index that's in this array. That's it. Yeah.
But isn't it supposed to be messages of 103, messages of 205, like object itself, like the whole thing, not just the index that up. Like inside this example, for example.
Yeah. I mean, there's no need to, because why do you want to save the actual message here? Or you want to save just a reference to it?
What if could you send the reference to it? Like with just a number. It could be any number. How does this
It
number
could be the
represent-
same object, or it could be a reference to it. What do you want to say?
Obviously, a reference is better
Yeah.
because we wouldn't repeat the data. But at the same time, like how is 103 representing that index? It's just a number, in like when we look at it, it's just an array of numbers to me.
Yeah, exactly.
So how
But
is
we
it-
know, like if we are building this, we know like this is the main data storage, which is messages. And we say, you have two interfaces to interact with this data. You have user interface and you have room interface. And you get to choose. Like if I tell you number 103, that means you know it's an index in the original array.
Ahmed, what if the message before 103 was shifted? Would the index also shift with it? Was deleted?
So let's say we delete 103.
Yeah.
What happened to 205?
What will happen?
I mean, we're designing this now. What's your solution to this problem?
Yeah, I was thinking like delete the index but keep it as delete
Yeah, I mean, you could do this. It depends on your needs. Like some people say, delete is soft delete. That means in databases, and you will see this a lot in industry. There's nothing called hard delete. You should not delete any piece of data in your database. So you label it as
Absolutely.
deleted, but you keep it there. Okay? So you deleted it from here, for example. You go here, you delete it, or you kind of like you can put it in an object, and next to it there is a label deleted or not, true or false. Okay? But if you're doing hard delete, which is deleted physically, you need to shift everything up here, and you need to shift everything to the left. Yeah.
Those indices on the right side of the hash table will be output in the RAM or the disk or the RAM?
Well, and this, since we did not get to data persistence yet, this is only around the RAM. We're gonna move this data to our disk now, and this is where your guys are struggling.
Serialization.
Yeah. Yes.
The hash table take all the message, all these messages, and when you give it the input bar, for example, it gives an array of bar.
Yes. Array of messages in the loom part.
Yeah, but the hash table itself take all the messages to analyze.
The hash table itself take all the messages, so all the indices.
All the
Indices. See? Yeah.
the indices is the output.
Well, arc itself is a key. That's the room name. And the value is array of indices that points you to indices in messages.
Yeah, but the hash table points depends on it takes the whole array inside it.
No, it takes indices only.
Indices.
All of the indices, they should exist here, in this part, in the values. Does that make sense? It's just a way to represent data, and it's just like has better complexity. Okay, back to serialization. This is usually the most difficult part to explain to people because, and I used one of the lectures I did this lecture twice, cohort 4 and cohort 3. And in cohort 4, I just skimmed through the second part and get to the result directly because I got a lot of questions. And yeah, I mean, some people, there is two ways of understanding a topic. One of them is just focusing on every single detail because we're just exploring options here. And I'm sure like whoever designed this lecture, it's kind of, some of them is like useless. But another way is just to say, get the general idea and see the conclusion. What did we end up with? Okay, so let me skim through this quick, and then I will stop and I'll let you ask questions. Okay? So, again, here they are just exploring stuff like, what can we do here? No, before that. I jumped directly. So the question here, what values are indices referring to here? What are we referring to? Indices referring to message objects, they say. So every index here refers to specific message objects, and then to serialize an index means we must serialize the message object too. So we need to serialize the message object and serialize the index. But serializing messaging objects from indices is an issue. So you want to go to every index, see what's the message, serialize it, and add it to the memory, to the hard disk. But that means message objects are also referenced by the messages collection, or the message collection, that are already serialized. So you're kind of like doing stuff. Even you're serializing the whole message and add a reference to it here. The reference could be an index, the reference could be the object itself, the reference could be a serialized memory location. So there's many ways to do this, But whoever wrote these slides jumped to the pure idea, which is I'm serializing the ID itself. What's the ID in this case? It's just an index. So array indices. So that's the end result. You jump to the end result. But whoever like hacked Reactor tried to explore many things. So what we do here, IDs are agnostics of the data itself, and records are always addressable. I have no idea to their IDs. Using IDs instead of object reference, so you don't need to use the object reference itself, which is could be memory location, it could be some location in the hard disk. You just reference the ID itself, which is the array index, and that's it. And that should be the solution instead of like doing serializing the object itself. So let's do a conclusion. So this one, how do you do this? Easy. You take this, serialize it. So you put, before you serialize it, you put the indices here. Okay? So you have how many objects here? 3. You serialize this, you serialize this, you serialize this. Save them to the hard disk, and that's it. How do you serialize them? You just convert them to JSON. So JSON, JSON, JSON. You have 3 JSON objects. You put them in the hard disk. When you read tomorrow, you read them, you parse them again, you'll get this data structure, easy. Yeah, you get arrays here with keys, and you get the original array. And then you have the same data you saved yesterday. As simple as that, okay? So, is there any confusion at this point?
The problem is when we say it's so easy, but we really want to implement what? From where to
Well,
start?
I at the beginning of the lecture I said you will not implement this.
No.
Yeah. But it's very important to understand how it's built. Okay. A couple more things because we don't want to take longer than 1 hour. So one of the problems, so we solved the first problem, which is addressing the data in multiple ways. The second one is, can store more data than can be held in memory? We have just small size of memory. We have big hard disk. We want to save this in the hard disk. Like we want to keep add and add and add. So this again will be saved somewhere in the memory. Let's take the original messages. Our messages have been persisted to disk, saved to disk, and it's serialized. We know there's more data than can be held in memory, and some records are not in memory. At any moment, we could be asked to load one of these messages. I want to load one message, or I want to load all messages. So it depends on what we want. How do we identify the record? How do we do that? So we say, okay, load message 417. Remember, go back to here. Let's say I read these, only these, not this, that. The references. I read them to the memory. Let's say I read user, and I want Pamela messages. How do I get Pamela messages from here? Should I load all of that into here, or do what?
Just load the messages that Pamela sent by referencing the array of the messages that she sent to the indexes.
Yeah. But the problem is, that's cool, but the problem is, this is like serialized already.
Oh, we have to
It's
unserialize.
JSON, unserialized. Let's see, how to identify a record by its ID. Yes, we pass the ID, we say go, unserialize it, and pass the index directly and find it.
Don't we have 3 objects?
3 objects. Yeah.
So we just can pick the object that has the ID of the one that we're asking for
And
just
we access it. Yes, yeah. That's exactly what's going to happen. But finding the record on a disk is a little more challenging. Here, in this example, they're assuming you're not loading the whole data into memory. You want to go access this specific message in the hard disk and get it back. It's going to be hard, right, to do this because this is already in the hard disk. It's not memory. So arrays use an equation to calculate the actual location in the memory, but not in the hard disk. Okay? When data is persisted to a disk, records vary greatly in length. It's gonna get bigger because they have different locations now. Unlike arrays, records begin in irregular boundaries. So in memory, you have just array with specific boundaries, but in hard disk, it's very big there. We know time complexity of searching is big of n linear time to search for this here and go dig deep until you find a piece of data, and that's not our goal. Our goal is to get something constant. Okay? So how can we get big of 1 for disk lookup
Are you trying?
without loading the whole data into
Are
memory?
you trying to parse exactly what you want?
Yeah. So we're trying to parse this specific message, not the whole data into memory. How do we guarantee that?
I don't know if you can perform any logic on a stringified object.
Yeah. Could be.
It's all a string, right? Now in the hard disk it's a string. Are we gonna fetch that base?
Yeah.
It's a string. Are we gonna just catch this particular object?
Yeah, but this could be a string of 2 giga. Are we gonna load that into memory, the whole of it? I want to access specific message, and I know the index of it before serialization. How are you gonna do that? Otherwise, you should run a loop inside your hard disk and just keep checking until you find this specific text.
But you can't. Like,
All these.
what I'm trying to say is, how do you perform JavaScript logic on a JSON stringified folder, a file? You can't do that.
But you should load it.
Depending on the way that you serialize the object itself. You serialize every row and line, so you go directly to the line, which is the ID, or the index itself.
Okay.
Or if I serialize every object inside the file, so I go to the file itself. It's depending on the way how you serialize it.
I mean, what I'm saying is, let's say we have this data in a big JSON that's like 3 gig, and we saved it to the hard disk, right?
One file.
One big object called messages, big array that converted to JSON and saved in memory, in the hard disk. And now, when I have this in memory, and I want to get messages of lobby, could be 3 messages only. Okay? How can I get these out of this big data? Without loading the whole data into memory. So that's big O of n. Because you should, the indices change. They are now addresses in hard disk. Addresses.
They have to use,
Could be.
ID number, which is for every one. So the ID will be for everyone. It's like that.
Same as the hard disk.
Yeah, I mean, it's unique before we even stored it. It was indexed in an array. But when we saved it to the hard disk, now it's disk location, right?
so are you saying we have to use the file system to fetch it?
Let's see what's the solution. So how do we guarantee?
Another hash table? Come on!
She said it. Yeah. She said we have another hash table that map every index in the array into a memory location or a disk location.
How do you do that? No, seriously, how do you do it?
You do it.
No, I mean, we did it before with the JS file. Now we're doing it in a JSON format. Like how? Like we're going beyond like.
Yeah, it is beyond.
No, this is a like.
So let's see the whole solution. I'm gonna jump to the whole solution. That's the whole solution.
You're performing
Okay.
logic on a JSON file, not a JS.
You load it. Yeah.
Without parsing or anything.
Yes.
Wow.
So let's say this is the original data, right? And this is the original data before serialization. So we have this, and now we convert every single array location here, index, to some ID in the hard disk, and we punch the data there. And we say, we say 415 index of the array is this memory location in the hard, is this disk location. That's it. So we say, if I tell you, give me lobby messages, what do you do?
Give me log messages.
You go to this array, right?
Yeah.
You have 3 messages. You take every one, give it to the hash table, to this hash table. It will give you 3 disk locations. Big of one, big of one, big of one, done.
And it will parse exactly what you want.
You don't need to parse, you just read it, and it will to be read as string, you just convert it to
Parse whatever I
JavaScript.
So if you want to move this information from hard disk to different place, that hash table should be updated.
Yeah, exactly, for sure.
Second one.
Any change should be updated, yes. Okay, that took so long, so does not rewrite all state in every change. So suppose you want to change a specific record, we need also to change its memory location because it could be get bigger, like this bigger. Now the message is deleted from here because it's bigger. The assigned, the storage, it's bigger than the actual message size. So we just move it to a different one and we just change this value, which is the memory location. Okay? Indices must be persisted to. So if you change some index, for example, also you should change the memory location or the disk location. Prevents information from power loss. This is free because it's a hard disk. That's it. You just created MongoDB. That's how they created MongoDB. Again, you will never ever do that.
But you just have to
But
understand
this
how-
lecture is super duper important. Seriously. It's super important because you should know how they created this stuff. And what did you get out of this lecture? Not only how they created, you get how to do a mix of things, like using a hash table with an array to point to another hash table that does something saved in hard disk. This collection of information is super important to you.
We know the concept, but implementing it
You're not going to implement it at all.
isn't. Yeah.
People spent like months and years, I mean, I don't want to say years, could be months to implement this. We were trying to implement it in one lecture, and that's not going to happen, guys. Yeah. Okay? Well, they invented JavaScript in a week, but MongoDB, I think it took longer.
What do you mean they?
Yeah, for the hash table, I think it's a big hash table, which consists of 2 stages, right? The real action. Be one hash table consists of 2 stages.
Yeah, could be.
The seed one from the hard disk itself. I mean, this is how the data picture. Did it?
Which ones?
The whole picture now, we have 2 hash tables, but actually it's a one hash table, it consists of 2 stages. Each time you are looking for information, you will go for this process.
Yeah, that's the way you see it, but it's better to be 3 separate hash tables in this case.
So three
I mean,
objects.
n hash tables for n ways, n number of ways we want to represent that hash. Plus, you need 1 hash table to map between indices and disk locations and the actual data.
Yeah, about parsing and stringifying the data. So between RAM and the storage, which is the hard drive. You say we want to take exactly what we need. We don't want to parse the whole thing. But about the users in the room, we have to parse the whole thing, right?
Users in the room?
Yeah, like in order to.
Oh, you want to load it?
Yeah, you wanna
Yes,
load
you
it.
should load everything.
And then check
Good,
the
good,
data.
good question. Yes, he said this data we should not load all of it, like we load whatever we want. But this data,
We should
yes,
load all.
we should load it. Like, you know why? Because this could be like the big object.
Yeah.
A lot of data, lots of keys and values inside one object. So in this case, we have only user, text, and room, but it could be bigger and bigger and bigger. It's a big object that represents one piece of data. But here you're just having indices. So this is going to be light.
This is-
Okay, most useful parts, SQL and beyond. Quickly, differences about SQL. This is very important to remember, so please pay attention. If you got tired of that, like we're gonna need 5 more minutes to talk about SQL and tell you more about. So SQL, NoSQL, DBMSs, database management systems. 2 types, NoSQL and SQL. NoSQL is what you just saw, JSON. You just push JSON in disk. SQL is something else. Okay? So they are similar. So they're both data storage techniques, except NoSQL database using ID index to achieve big O of 1, right? So we use an index to hash it and give some memory, some disk location. It's big O of 1. SQL databases use array-like technique to achieve big O of 1. To also give you big O of 1 by using arrays. We're gonna see it later. Not today. Not now, I mean. Okay? Today, but not now. So, yeah, that's NoSQL. So that's how we map. Okay? And that's SQL. SQL, they are saved in an array. It's a table. So each table has an ID. Okay? So you give it specific ID. And you put the rest of the data, but you give it an ID. That's what's special about it. Okay? But it's fixed size, fixed width. It's fixed width, but it's not fixed length. It's going to be constant time. That's how they built SQL. Now they are, huh? Yeah. I mean, but it's fixed. Yeah, it's always going to be fixed. But in NoSQL, you can punch any data you want. Now, SQL is faster in computing relationships. You'll get this afternoon. Like, what's relationships? How do we... Actually, you read it in school, when you do school. So, it can skip ID indexing step. There is like some step that's skipping, which guarantee to you like the goal of 1, so it's faster. Record stored in a binary format, not JSON. Just compare everything to binary and bunch it to the hard disk. In NoSQL, field must be parsed to find a separator and identify individual fields. So you must parse the data. But here, there is no field separators. Fields are always in the same location every record. So they give it to you like this. It's a 1 row, and each one has a static location. The ID is always to the left, and Fred, the user, and the text in the row. Okay, it's a table. Think of it as a table. It has headers. Some NoSQL databases that are not all similar to SQL. Some NoSQL databases are not at all similar to SQL. Yeah, I mean, maybe you'll see some similarity, but some of them are completely different. They implement things in different ways. That's it. We'll talk about SQL today, and you'll see what's the actual differences, because it's completely different. And I think, in reality, in industry, we use SQL more, because that's what industry uses. Industry does not use NoSQL a lot. They use SQL because it's easier to use, more flexible. It's like a table-like. It's easy to understand because it's a table that has headers, as you see here. And the visualization of the data is also great, because if you open the SQL database manager system, you'll see it as a table.
Like an Excel.
You won't see it like this.
Excel file, like something like that.
Exactly like Excel file. You'll see it as Excel file. Okay? Do you know, like when you convert JSON to Excel, you'll see it as Excel. You see it as table. So the same way here. In SQL, you see it as tables.
Somehow, the SQL is like a binary search, like using calculation, how to get the things manually.
Yes.
Somehow.
The mathematic way is using ID. Every entry you need has specific ID. So you access, let's say, I will give you just a small example. If you go to the bank, what do they take from you? Like, how do they know your identity?
The ID.
Your account number,
Yeah,
right?
account number,
So they just put your account number, then hit enter, your data will come fast. Each ID, so this is called an ID, so it goes to the left here. It's unique, it's saved in a specific index in that big table, and there's some kind of, this is like, it's not part of the lecture, but there's some kind of magic that happens, convert your ID to that table ID. Yeah. So they kind of use hash table in a way. Yes.
My question is that you mentioned that in NoSQL data we have to parse.
Yes.
But in SQL, what do we do?
There's no parsing. You read the data as binary, and it will be
So
converted
it's
to
like a
string.
TXT or like what kind of data are we saving it as in the hard drive?
The hard drive is binary, zeros and ones.
Oh, binary.
Yeah.
So how do they actually see it?
The computer will take care of that. Like you don't do that. Yeah, don't worry. Yeah. Seriously, like the computer will do that for us. We're not gonna convert binary to string. That's hard.
So it will convert it to this format. Like
Yes,
Okay.
exactly.
Interesting.
Any other questions? Or move on. Who got 80% plus out of the lecture? Seriously, be honest. 80%. That's cool. Good. Who got like 50 to 80? Who got less than 50? Be honest. Okay. 2. Yeah, that's not bad. So average is 70%. That's cool. Yeah, I mean, I'm glad that you got 70%. Cool. So we get more of this like when you do the exercises. So this afternoon again we'll talk about SQL. We'll focus on SQL a lot because I know you did not like NoSQL at all. I'm sure you did not like it. But you know what's surprising? What's surprising is when it comes to projects, people use MongoDB more than NoSQL. Yeah, but advice from your brother: learn SQL more, use SQL more. When you do your project, use SQL. Don't listen to anyone who tells you use MongoDB because, Mongo's NoSQL. Use SQL. You have three free SQL. You have SQLite, you have MySQL, and you have Postgres SQL.
These are programs.
Postgres. These are database management systems, 3, and they are all SQL. Use them because this is what will help you in the industry, not the MongoDB.
What about the SQL Plus?
There's many of them. SQL Plus.
Yeah, we used to.
There is SQL Server
No, SQL
from
Plus,
Microsoft.
like SQL Plus. We used to use it at the university.
There's a lot of them,
Like, they are all
but these
SQL.
are 3 free. I'm not sure if there's other.
It's money too.
Yeah. You said yeah you mentioned to me yesterday. I'm not sure. Is it free? Pioneer. It's SQL, right?
So I can use that.
And SQL has become famous in the cloud.
I mean, I don't know. I don't prefer use it. I did maybe 100 interviews in industry. I was in charge of outcomes. So in core 3, I was in charge of taking people, placing them in companies. So that was my job in core 3, in addition to lecturing. So every company I met with, they use MySQL or SQL Server. I didn't see anyone who using MongoDB. But you might get an interview that asking you about to use MongoDB. So it's worth you learning. So learn both. But when it comes to your project, it's good to use SQL.
Which one is using?
SQL. For sure.
Maybe more than they have a big share of
Yeah, it's SQL.
it's expensive.
Yeah.
It's really,
Yeah, I agree.
Why is it expensive?
It's very expensive.
I mean, SQL is more expensive than NoSQL, always.
Yeah, for commercial thing, Oracle as a database management system. To buy it, we bought from.
Yeah.
I was recruited before. We bought it's very expensive. The most expensive one.
Super expensive.
Yeah.
Yeah.
It's like SAP, mostly SAP and
Yeah.
Oracle.
Yep, I agree. By the way, there is like a couple of developers who created their database management system,
They're by themselves, custom.
and I'm not sure what's called. They built something and then they created it, and then so Oracle bought it from them. They paid them money, and then what they did, they forked the GitHub and created their own, and now they have it. So they cheated. No, they sell it twice. Yeah, I mean it's open source. They can do it. Where is you? All right, guys. Thank you so much. See you this afternoon. Thanks.
All like built in. You don't see it. You don't interact with it when you interact with the management system, right?